In this video, we're just going to talk about augmented matrices and how they help with systems of linear equations, and we will also talk a little bit about row operations. I won't get into any specific examples of what Gaussian elimination is until the next video. So to begin with, I want to define what an augmented matrix is and how they help us with systems of equations. So a system can be rewritten as an augmented matrix in the following way. So what we can do here is first set up our matrix with our brackets. So I'm going to have some brackets that look like this. And essentially all we're going to be doing is taking out all of the operations and variables that are incorporated with this system of equations here. And how we do that is we just go straight left to right. And the first number I'm going to write over here in the matrix in the top row will be 3, because there are 3 x's in the first equation. The next number I will write in this matrix here will be 2, and that is because there are a positive 2 y's in the first equation. And in the third spot here in the top row, I will write -5, because there are -5 z's. And in this last spot over here, I'm going to write 0. That's what the constant is. So how we can break down this matrix is that anything in this column will represent an x over here in this system. Anything in the second column will represent y's. Any number in the third column will represent z's, and anything in the last column over here will represent a constant. And then I drew this vertical bar in here without saying anything about it. This represents our equal signs. So I have this here just to make sure you guys can keep track of what's going on here. X is in the first column, y's in the second column, z's in the third column will equal some constant. So the next equation, if we were to write it over in the matrix, would look something like 5, it's -3 z's like we have over here, and 2 like the constant we have here. Now the problem is we don't know what's here. Well, actually we do know what's here. It's nothing. There are no y's in this equation. So if there's a missing variable, we can't just leave that entry in the matrix blank. We have to write something there. And every time you have a missing variable, we will be writing a 0 in that place. So this third equation, if you look, there are no x's. So we know there will be no x's, 19 y's, 1 z, and 20 for the constant. So this is how we can write a system of equations as an augmented matrix. Before we get into why an augmented matrix is helpful, I first want to solve this system of equations right here. Now this system of equations is set up really nicely because we already know what one of the answers is. So I'm going to start my answer over here. I'm going to start my answer. I know as an ordered triple, because I have 3 variables, I need 3 numbers in my ordered triple, that z is 2. So I'm going to put 2 in my answer right away. Let's see, how can I figure out x and y? Well, since we already know what z is, I'm going to take it back one step and substitute z into this second equation that I see here. So that'll give me something that looks like this. So here's this equation, 4y plus 3 times z, but instead of z, we're going to be writing 2 in its place, equals 10. So what I can do now is simplify this to 4y plus 6 equals 10. And if I go through and do all the rest of the solving, you'll see that y will equal 1. And so this is another piece of the puzzle that I have now. I know z is 2 and y is 1. So I'm going to put my answer up here. Y is 1. And now that I know z and I know y, I'm going to take these variables and I'm going to put them in this equation and solve for x. So what I did was I, again, took 2 and substituted it in for z in the first equation, and 1 for y and substituted it in for y here. That's what this equation represents. So now all I have to do is simplify all of these constants. So 2 times 1 is 2, minus 5 times 2 is 10. So 2 minus 10 is negative 8. So this becomes 3x minus 8 equals negative 5. And if you go through and solve this for x, you'll get that x equals 1. And so this is the last piece of the information I was needing for my answer up here. Now I know all three values. X is 1, y is 1, z is 2. And I can write that as an ordered triple, 1, 1, 2. Now I also want to take a second and write this as an augmented matrix. I'm going to do that right down here in this little space. So here's what that augmented matrix looks like. And the point I want to make here is this system was very easy to solve. And that is because you'll notice here in these blank areas, there are no x's in either of these equations, and there's no y in the bottom equation. Those are represented by these zeros right here. So if we can figure out how to get zeros here, or how to eliminate x's and then eliminate a y, right? We eliminated x's from these equations and the y from this equation. Then we should be able to turn a matrix back into these equations and solve it very simply. And that is the idea behind Gaussian elimination. Not all systems will be set up as nicely as the previous slide. So what will happen is this. We will rewrite the system we're given in matrix form as an augmented matrix. So something like this: 1, 2, 3, negative 3, negative 2, negative 3, negative 1, 2, negative 7, 1, negative 5, and 20. And what we will do is we will do some math operations within this matrix to get a matrix that will look something like this. Then from here, we can rewrite this matrix back as some equations. Let's see, that would be x plus 2y plus 3z equals negative 3. You can see how I did that. There are x's, y's, z's equal a constant, just like we have always done. It's just now changing it back from a matrix into an equation. So 1x plus 2y plus 3z equals negative 3. The second row will represent a different equation, this time with no x's. So I'm just going to start with 1y plus 3z equals negative 4. Oops, plus 5z. And then the last row down here, 0y's plus 0x's plus 1z equals negative 1. So we will just write z equals negative 1. And then we can solve this very easily like we did on the last slide. And so right now, this red arrow here is just sort of magic. But we do that magic all within the matrix. And we can do this magic by performing row operations. One last thing before I get to the row operations I hadn't mentioned. These zeros are here again, And so being able to create a zero within a matrix wherever you want that zero to be is going to be a very important skill to have. But even better, the example on the last slide, I didn't get to mention this because it wasn't set up nicely for it, but this main diagonal here will be ones. So we'll have a main diagonal of all ones. And that's going to be really key. Those ones are going to help us in this matrix get the zeros that we need in these specific places. So we can't get these ones and zeros unless we have row operations. So here are the row operations. There are three basic row operations, being row swap, row multiplication, and row combinations. So I mentioned in the previous slide, we like having these ones and zeros, and two of these row operations, the row swap and row multiplication, are good for getting ones. And the row combinations are what we like for getting zeros. And so over here in the red ink are just what row operations look like. This does not include any of the math that will be done with these row operations, but that's what these row operations look like. So for example, a row swap has two rows, any two rows. I just picked the number 1 and 2 this time, with this double-headed arrow in between them saying switch row 1 and row 2. Now the way I teach this, you only want to do this one at the beginning, or generally never at all. And these rules change if you go up into linear algebra, but this video is meant for college algebra students. So it's either you do it at the beginning or you don't do it at all. Usually the matrices are set up in such a way that you do not have to row swap later on, at least where I teach. The second row operation is row multiplication, and generally that means you're going to multiply a row by a number and then replace that same row. So if I want to multiply row 1 by 5, that's the top row by 5, then I'm also going to replace that row 1 with that new row. The other way to think about it, and which will most likely be happening more often than not, is that we need that row to be divided by some number. So we can write out for now that row 3 would be divided by 2, and we would replace row 3 with that new row. And lastly, we have row combination, and that's when you multiply a row by a number. I say S, row S, because I don't know what row you're trying to multiply by a number. Row S by some number, add it to another row, and that second row is what gets replaced. And this is how we get zeros. You can only get zeros if you're adding or subtracting. The row multiplications, you can only multiply by non-zero numbers. That's why I picked 5 and dividing by 2. If you multiply an entire row by 0, that just blows up the matrix and doesn't help you in any way solve the system of equations. So that's it. That's the introductory lesson for augmented matrices and row operations. I hope this was helpful.